In this video, we're going to check out the momentum model for this collision of a 2 kilogram cart moving to the right at 4 meters per second and a 1 kilogram cart moving to the left at negative 5 meters per second. Notice that direction is important here. So that we put a negative sign because the object's moving to the left. After the collision, the 2 kilogram cart is moving at negative 0.5 meters per second, and then the 1 kilogram cart is moving to the right at 4 meters per second. Then we draw our interaction diagram. So each object has a normal force and a force due to gravity that they experience from the Earth and the surface. In addition, they experience a normal force between each other when they collide. So if we look at the 2 kilogram mass, it's got a normal force upward and a force due to gravity downward, with a normal force that makes contact with the 1 kilogram mass. The 1 kilogram mass likewise has a normal force upward and force due to gravity downward, with the same normal force when it makes contact with the 2 kilogram mass. It's equal in the opposite direction. So that's obviously a third law pair, as we would notice here between any of these black or dotted lines. There, any force between them is a third law force. So if we look at the momentum using this graph, we use the vertical height as the velocity and the horizontal as the mass. So in other words, we're using area to represent the momentum. So the 2 kilogram cart is two of these blocks across, and it's moving 4 meters per second before the collision. So 2 times 4 makes an area of 8 kilogram meters per second. And again, we make sure we keep the right signs there. The 1 kilogram mass, it's got a base here of 1 kilogram and a height of negative 5 meters per second, making a momentum for it of negative 5 kilogram meters per second. So what we do with the momenta is we add them together. So this 8 kilogram meters per second and this negative 5 kilogram meters per second add up to 3 kilogram meters per second. We have no net outside force, and the reason for that is these two forces, the force due to gravity and the normal force, as we can see, balance out on both the normal force and the force due to gravity for the 2 kilogram mass, and the normal force and the force due to gravity on this 1 kilogram mass. After the collision, the 2 kilogram object is going negative 0.5 meters per second. So now we're using a height of negative 0.5 meters per second, a width here of 2 kilograms. So 2 times negative 0.5 gives us negative 1 kilogram meters per second for the momentum of the 2 kilogram mass after the collision. For the 1 kilogram mass, we still have that base of 1 kilogram, but now it's got this height of 4 meters per second. To find that momentum, we multiply 4 times 1 and get 4 kilogram meters per second. Just like we did here before the collision when we added up the positive 8 and negative 5 to get a total momentum before the collision of 3 kilogram meters per second. After the collision, we do something similar. We take the 4 and the negative 1 to get 3 kilogram meters per second. So we notice that the momentum at the end is equal to the momentum at the beginning, and we say momentum is conserved. So in my coordinate system, I'm going to say to the right and up is positive. The general equation we use is the initial momentum plus the impulse is equal to the final momentum, and that looks like this. This represents the momentum of the blue cart before the collision, the momentum of the red cart before the collision, the impulse, which there is none, and that equals the momentum of the blue cart after the collision and the momentum of the red cart after the collision. And later on, we will be using other values in other problems, and we'll be using that equation right there. All right, so let's also look at the kinetic energy of both objects before and after the collision. So the blue cart, we find that it's got 16 joules of energy before the collision. The red cart, we find that it has 12.5 joules using our equation 1 half mv squared to calculate both of them. We add those together to get 28.5 joules of total kinetic energy before the collision. After the collision, we get a kinetic energy for the blue cart of 0.25 joules and a kinetic energy of the red cart of 8.0 joules. We add those to get 8.25 joules. So notice our total kinetic energy has decreased from 28.5 to 8.25 joules after the collision. So if we ask ourselves, is there an outside force and how do we know? We say there is no net outside force because the normal and gravitational force on each object balances out. Like we said here with this normal force and that force due to gravity, and that normal force and that force due to gravity. These forces here are not transferring any momentum or any net outside force into our system. Is there an impulse and how do we know? There is no impulse because there is no net outside force. An impulse is an outside force that gets placed into our system, and here we have none. Is a collision completely inelastic, elastic, inelastic, completely elastic, or superelastic, and how do we know? So we look at this chart here and notice that this is an elastic, inelastic collision as kinetic energy goes from 28.5 joules to 8.25 joules. But the maximum amount of is lost as the, but not the maximum amount is lost as objects do not stick together. So it's definitely in here and not in any of these other locations or within the spectrum. Is momentum conserved and how do we know? Well, we can say this in several ways. Momentum is always conserved in a collision in which there is no net outside force. So the only force that's transferring momentum is between the two. Momentum is always conserved in collision in which there is no net outside force, which would produce an impulse. In addition, the calculation of the initial and final momentum is the same, 3 kilograms after and 3 kilograms before.